Okay, it's about the time, so everybody get ready for the class. Okay, let's get the test, and I'll give some feedback next week. So just a very general, okay? So don't worry about that. Quiz is just for me to get some feedback about how everybody understands some of the fundamental concepts. Everybody got the name on the corner? Okay. So for the ERDIC, if you can have someone take a lead and take a picture of that and email me, that would be great. Yeah. Thank you. Yeah. Okay. So we're now the week 2 of the September. So what we're gonna do today is continue to talk about chain conformation. Yesterday, I left it a teaching tool in the graduate student class. Everybody got a chance to see it? I left some molecular model for you guys to understand what is hindered rotation model, or what's the rotation between different chains. Okay, and it's for you guys to play a little bit with it. So a recap of what we taught last class. So what we did last class is to discuss about free joint chain model. So we talked about, for the free joint chain model, how it is difficult to use end-to-end distance to get the final value of the chain conformation, because average of a chain n as a vector is equal to 0, so you wouldn't be able to get much statistic information out of it. So instead of using that concept, we discussed about end-to-end distance and how can we use end-to-end distance concept to describe a length scale of the polymer chain, right? So what we did as a recapture, so we discussed free joint chain model. So what free joint chain is basically a model that as simple as describing a chain in 3-dimensionally. There's no limitation in the rotation or movement of your bonds. So it can rotate very much freely in 3-dimensional space. And this is the most simple model, very easy to understand. And we talked about the concept of end-to-end distance, and pretty much what we quizzed today. Right? So end-to-end distance, if we follow the format of what we write, REE, for free joint chain will be equals to NL squared. N is number of bonds. L is of what's the length of each individual carbon-carbon bond, right? So NL squared. Quite straightforward. But this is the most fundamental model. It's most simple to understand and most easy to study. So now today we're going to do something a little bit more real. We want to understand how actually different bond angle influence your end-to-end distance or overall dimension of your polymer chain. Okay? So this is a little bit recap what we talked about last week. End-to-end distance will equal to, the self-term, and this is a cross-term. And because of free joint chain, we pretty much eliminate all the cross-terms. So what we left is a self-term. And if you count how many of these self-terms, it's actually NL squared, right? Number n. Each R dot itself will be L squared. Okay? So any question on what we talked about in the last week? Okay. No? Everybody did a good job, looks like. So if I want to tell you, now we need to get a little bit more realistic. What would you guess would happen to the polymer chain, and what kind of consideration we need to give for a real polymer chain? I heard bond angle. Interaction. This is a very much broader term. So in our case, we do not consider intermolecular interaction. So it's pretty much a chain itself, and we don't consider the interaction between different segments. It's pretty much no interaction with anything. Okay?
Conformation is studied as Gaussian trans.
Conformation. So that's like rotation potentials between different chains, right? So for each two of the for each two of the interaction, we actually will came up different model. So the overall goal for today's class is to study free rotation model. Okay? The goal for us to understand if we consider a bond angle between different segments, how it actually influences the end-to-end distance or overall size of your polymer chains. Okay, this is one part, free rotation. And second part, if we have enough time to get to, we're going to get to hindered rotation. Okay? So combined with the free joint chain model, we will have total of 3 different chain models to describe our polymeric material. So again, I want to refresh everybody the different bond modes we would have using the toys. I get everybody, you now be able to rotate this particular bond and see how this would rotate in 3-dimensionally, right? So actually, all the black, those kind of teaching tools have 4 bonds and represents a carbon atom. And the white color represents a hydrogen. So if you stick them together, this would be 1 carbon, second 3 and 4 carbons along the polyethylene hypertheoretically. Okay? What's the bond angle typically you would have? Yeah, about 109 degrees, right? Then, while we fix this piece, we don't move. While we only rotate these bonds, we can actually start creating this dihedral angle. And dihedral angle is basically how much rotation you could have. And again, for the end-to-end distance, we can just use a simple expression. We use a vector to add every single bond together. We get a vector of the end-to. We get the final vector sums or the projection, right? So what I want to point out is if you look at this particular schematics, what we highlight here is a gray zone which highlights the relative angle between the projection of this bond versus the next bond. And the angle which shows beta should be equal to here, and it's 2 pi minus 109 degrees. This should be around 71 degrees or so. Okay? So what this does is say how much projection you would left along the original direction of the polymer chain. And this is basically a cosine component of what's the next bond. If you keep going, if there's one additional component here, it will also have some projection along this original bond, right? And how much projection it would have is equal to L cosine beta square if you have second bond. So the more bond you have, you start to lose, the degree of persistence around this original direction. So if we play with the toy, we hand it out in the graduate study room, we will see the longer the chain is, the less clear for the future chain will follow the original direction. The chances it's deviate from where we are actually going is much higher, right? And in the other direction, this is a dihedral angle, which I will talk more in the hindered rotation model. Okay? So in the free rotation model, we only want to consider if we now fix this beta to a certain angle. how this would affect the end-to-end distance. So I need a volunteer and someone guess. So what we know in the free joint chain, we know REE square, or end-to-end distance square, is equal to NL. For free rotation chain, what do you think this REE would be equal to?
NL squared.
Compared to this one?
NL squared plus
NL squared plus
1 plus cosine over 1 minus cosine.
1 plus cosine and 1 minus cosine theta. I would take this away. Just can someone explain to me what this means, since you speak out? This is the correct answer, but what's the physical meaning of that? Is that
proportional by some sort of constant.
good answer? So let's first explain the physics meaning of that, and we go into the detail of how we actually get this. Okay? So let's look at this part of the equation. So we know NL squared is equal to this part, right? It's the same as free joint chain model, but for free rotation chain model, where we now start to have additional components come into play, and this particular component is 1 plus cosine theta and 1 minus cosine theta. Depends on different textbook, they actually define theta differently. So I'm going to talk a little bit more in the detail in the slides. But if, let's say, theta is a 60 degree, this will be a constant, right? Cosine theta will be a constant value. So you're going to have, this is fixed. And depend on different theta, this value actually changes. And I'll just jump into the slides and talk about that. Actually, if you guess intuitively, if this bond angle is beta gets smaller and smaller, how big your chain? Will it grow bigger or shrink smaller? It will grow bigger, right? Because then you have always chain bonded into one particular direction. Yeah, Sonia, question?
I'm sorry, I still don't understand why we put the 1 plus cosine theta and 1 minus cosine theta there.
Very good question. I bet nobody here understands it. I haven't explained it yet, so this is just one of the conclusion I will jump into first, then I'll explain how we actually get there. The explanation is quite a little bit complicated in math, and I did it last year. I believe most of people sat through 30 minutes very quietly. So this year I'm going to do very differently. I will explain the concept first. What actually, if you fix the angle, what this does to your model and how does it affect your real space arrangement of your polymer chain, okay? So like I explained, if we start to fix this angle instead of let it rotate it around, you now start have the chain would follow the direction where its original intent to. In an extreme case, if you have this beta is fixed at 0 degree, which means your chain is always going to be straight, then you have a large end-to-end distance. But once this is start to rotate, getting smaller angle, your end-to-end distance will start to drop. That's a physical meaning. It's about when you fix a bond, how does it affect your end-to-end distance? And we will jump into that. And we talked about this already in the last class about in the free joint chain model, your end-to-end distance R squared will be equals to NL squared. And we pretty much understand why that's the case, because all the self-turn pretty much left and all the cross-turn eliminated with each other because there's no correlation between different bond angle, right? It's a free joint chain, so your positive direction of free rotation cancels out with negative direction, which ended up NL squared. Kind of very easy to explain. This model, it's as I just said, it's not in a physical sense, but it's very important as fundamental concept when we explain the polymer physics, because this is most simple and easy to follow. So we need to experimentally apply this only to the long chains. For the short chain, it doesn't necessarily follow this statistics, because one of the assumptions that is n need to be long enough for these to be statistically correct. Okay. Last point I will only talk about in the end of class, this particular thing called no excluded volume interaction. In real case, your physical chain would exclude another chain occupying the same space, so the overall size of the chain would expand. And I can only tell you now, in the real chain, it does not scale with NL square, but it depends stronger on the n. It's not 1, but higher than 1, okay? So which means in the real chain, your end-to-end distance will be expanded compared to free joint chain, because free joint chain allow you to overlap on each other. And we don't consider excluded volume for now. And if you go to read the textbook, in the polymer chemistry textbook, it's discussed in the chapter 6.8 when they talk about real chain or excluded volume. You might also ask the question that what if your ideal chain is not just as simple as always carbon-carbon bond in the backbone? How do we treat that special case? So this is a little bit interesting, and we can discuss this uses a theoretical model for polybutyl methylmosaccharide repeating unit. So in this case, you can see in the backbone, which dictates mostly how your end-to-end distance is, which composed with one. This is the one bond, this is the second bond, right? They are both carbon-carbon bond, but they will take slightly different. The same formulation, the self-term will stay. It doesn't matter what bond you have in the backbone, but the same mathematic applies. So in this regards, your end-to-end distance can be as simplified as RE square average will be equals to how many bonds of carbon-carbon you have in the backbone. What's the length of carbon-carbon bond with carbon-oxygen bond and carbon-oxygen. So this actually represents, one of them represents carbon-oxygen. So in this PEO repeating unit instead of the last case, okay? For the PEO, you would have a carbon-carbon bond and carbon-oxygen bond in the polymer backbone, because each repeating unit will be different. And the same mathematics applies to this. Okay? It's just an example for you to understand, instead of polyethylene, the same math can be applied for polyethylene oxide, for example. Even the backbone has different components. But in a nutshell, only matters a little bit because carbon-oxygen bond just a slightly difference in the length. Okay? Now comes into free rotation chain. So this is the final formulation. Actually, some students already started early, and this is what we would get in terms of what the end-to-end distance. RE will be equals to NL squared, 1 plus cosine beta, 1 minus cosine beta. Okay? And beta, in this particular case, is this angle. Okay? This angle is beta, and this is theta. Some of the textbooks do it differently. If you saw 1 minus cosine theta, 1 plus cosine theta, it's the same thing, because cosine beta will be equals to minus cosine theta. That they're kind of depend on who wrote the textbook is slightly different. I'll come back to this cross term because fundamentally this equation is universal when we discuss the end-to-end distance, right? So this doesn't matter what type of chain model you use. End-to-end distance will be always the self-term plus the cross term. And in the free joint chain model, this component doesn't change. It's always NL squared. Right? Everybody gets it? Because this is self-term, you have total n, the number of n plus Ri dot Ri, and that's equals to L squared. Now, how do we treat this cross term? Now it matters, right? Because we cannot say, in the case of free joint chain, this would be 0, but in free rotation chain, it's not 0. I wouldn't talk 30 minutes to discuss all the mathematics we need to go through. However, I will upload a separate video if you are interested to understand details. How do we simplify this to this term? So in other words, if you always consider the cross term, you will be able to simplify this term into 2nl squared cosine beta 1 minus beta. Okay? I think it's a little bit outside the scope for everybody to sit 30 minutes just look at a board of equation. But I hope you guys, whoever is interested to get an A+ for the class, go to watch the video and understand a bit better how mathematically we got here. How this would influence the end-to-end distance, I made a table and a curve for everybody to understand. So again, end-to-end distance will equals to n L squared, 1 plus cosine beta, average, 1 minus cosine beta. So let's look at this curve. What are we plotting? Y-axis, we plot 1 plus cosine theta, 1 minus cosine theta. Okay, 1 minus cosine theta divided by 1 plus cosine theta. And this is the bond angle. From 0 all the way to 180 degree. So anyone tell me why I should care about this curve? Sonia, please.
It looks like once you get to a certain angle, that's the only point in which the distance can increase.
Right. So 1 is where equals to free joint chain model. In the free rotation chain model, if theta equals tan 90, it's a special